Now, it wasn't known a long time ago what light really was. In Newton's time, it was thought to be a stream of particles, little objects we'll call photons, little particles of light that stream out in a straight line, again, similar to the ray theory of light. But there were proponents of another theory called the wave theory of light, that light behaved as a wave. In order to prove that light behaves as a wave, one way to do that is to show that light undergoes wave-like properties. And one wave-like property is interference. If you recall, you can have constructive or destructive interference when you have two waves that interfere with one another in various ways. Constructive and destructive interference can lead to, when we talk about resonance in sound, where a sound is amplified versus a sound being diminished through destructive interference. So we're talking now about Young's double slit experiment. So famous scientist by the last name Young came up with a rather elegant and unique way to test the wave nature of light. He took coherent light, shined it through two individual slits separated by some distance, and then wanted to see if the light rays from each slit, or the light waves from each slit, would interfere with one another. If they don't interfere, it's a strong indication that light does not behave as a wave. If they do interfere, it's a strong indication that light is a wave. So we have to first deal with coherent light. Well, what is coherent light? You can't just open up two slits and shine a flashlight through it and see interference, because the light is not coherent, in that the light waves are not in phase, or there's no relationship between the light rays. For this experiment to work, you need coherent light. That's just light rays that are either in phase, they have their peaks and troughs in the same location as they move through, or they're shifted by some fixed but stable amount. If there is no connection at all between the phases of the light waves, we call that incoherent light. You won't see an interference pattern with incoherent light because the wavelengths are all over the place. The peaks and troughs are all over the place. So you can't form these interference patterns. So Young first had to create coherent light. Well, one way to do that is to actually just use a single slit, use Huygens principle, right? So if you have a very, very thin single slit, as light rays come and hit that slit acts as a wavelet, source of wavelets that spread in the forward direction. Now this light is coherent. You can then send that light through a two-slit experiment, where Huygens principle again states that the light will act as individual point sources and spread forward. Now we can look at the interference between these two point sources. So you have two sources, as I have drawn here. Each have the light rays coming out. Again, there's very small slits compared to the wavelength of light. If they're not small compared to the wavelength of light, this experiment doesn't work. So you have very small slits separated by some distance, and each acting with coherent light, each acting as a point source, those waves spreading forward, and when they reach a screen, you get what's called an interference pattern. What's happening is you take some part of the screen, you have the light coming from slit 1, you have the light coming from slit 2. They both go some distance. Depending on what the distance is, they might be in phase or out of phase. If their peaks line up and their troughs line up, they're in phase, and you get what's called, if you remember, constructive interference. The light gets brighter. But as you move up, you might come to an area, let's say here, where you can see the distance from slit 1 is shorter than the distance from slit 2. Since the light from slit 2 has to travel further, it goes through more wavelengths. And when they meet up at that point, slit number 1 might be at a peak, slit number 2 might be a trough. So when you combine those, you get destructive interference, or in this case, fully destructive interference. So depending on where you are on this screen, you will either get a bright spot or a dark absence of light. And that's called an interference pattern, and your book shows some examples of that. Also, most likely you will do an experiment using lasers and then double slit experiments. It's a very popular and easy to do experiment in physics lab. we'll be looking at, and lasers are coherent light. So we can replicate this experiment using lasers. Of course, lasers did not exist in Young's time. It's a relatively recent invention, but it makes the study of this very straightforward. So Young showed that light undergoes interference, right? You think that if you're shining light through these two slits, you would just get two bright spots on the screen on the other side. One bright spot, the top bright spot from slit number 1, the bottom bright spot from slit number 2. And that's what you would get for the particle theory of light, right? Going back, for the particle theory, if light are little bullets called photons, some of these photons hit the screen and stop. The other light particles pass through, and you would just get a buildup at two locations, right? One opposite slit 1 and one opposite slit 2. Imagine if I had a metal screen with two holes, you were firing a machine gun at it. Most of the bullets would hit the screen, but some of the bullets would go through hole number 1, some of the bullets would go through hole number 2, and they'd hit the target behind hole number 1 or hole number 2. You'd have two piles of bullets. That's not what Young saw. He saw at multiple peaks. He saw an interference pattern, which definitively proves that light travels as a wave. So Newton's time, they thought of light as particles. Young's time, he proved that light traveled as a wave. And later on, when we talk about Einstein in the next chapter, we'll learn that light is actually both. Light's very weird. But again, as you change positions on the screen, the path length difference changes. Path length difference is just how long does it take the light to go from one slit to that point compared to the other slit. So it causes the amount of interference to change. Now, if you want to know where do the bright interference patterns occur, there's an equation to calculate that. Now, I have it drawn out a bit here. This is a little crowded. So you have a double slit here with slit separation small d. That's the distance between these slits. Again, it has to be of order or maybe 10 to 20 times as big as the wavelength you're looking at. If this separation is thousands of times bigger than the wavelength, you're not going to see the interference pattern, or it won't be easy to see. So light streams across and creates an interference pattern. Now I'm going to take the central spot between the two slits and draw a horizontal line to the screen. So light that hits that spot between these two slits travels the same distance from each slit. So that light is in phase. So you get a bright spot in the middle. Now, as you move up and down the screen, you're changing the angle. So the angle is 0 here. You're going to some positive or some negative angle. If you want to know at what angle the next bright spot occurs, this is the equation to use. D is the slit separation times the sine of theta. Theta is the angle at which you can find the bright spot. Is equal to m. M is called the order number, and I'll talk about that in a moment, times the wavelength of light. So this experiment only works with monochromatic light. That's another restriction. Not only does it have to be coherent, it has to be of uniform color. Mono meaning single, chromatic meaning color. So you have to use blue light or red light or green light. You can't use white light for this experiment. Because the different waves, if you remember, blue light is a different wavelength than red light, which has a different wavelength than green light. If you want interference, you need to have the waves having the same wavelength. Now, lasers, nice thing about lasers, have the same wavelength. Red lasers might have 630 nanometer light, and it's fixed at 630 nanometers. So it makes this interference study very easy to do. M is the order number. It's just basically asking which bright spot are you looking at. The central order, the one directly across from the point between the two slits, is called the m equals 0 order, and it is always a maximum in an interference pattern. Or actually, and also a diffraction pattern, which we'll talk about a little bit later. So m equals 1 is always a maximum. Then you count up or down to see what the next orders are. So if m equals 0 is the middle order, m equals 1 is above it or below it. Now, your book actually defines the ones above as positive and the ones below as negative. Not all books do that. But just note that if you want to keep it all positive, like the equation I have here, m equals 1, 2, 3, and so on, 0, 1, 2, and 3, just note that that angle theta goes on both sides. So m equals 1 on the top has the same theta as m equals 1 on the bottom. m equals 2 on the top has the same theta as m equals 2 on the bottom, and so on. The only thing that's different is which side of the middle line do you draw the peak. Well, that tells you where the bright spots are located. What about the destructive interference? What about the dark spots where there is no light? Well, that's actually the equation below here in green. Again, fairly straightforward. The only difference is you have m plus 1/2 rather than just m, and m starts at 1, right? 0 is always a maximum. So you can't have 0 in here. Oh, my apologies. Because they added 1/2 here, you can use 0. So this is m equals 0, 1, 2, 3, and so on. So when m equals 0, this term becomes 1/2, and you can still see where the dark adjacent fringe to the central maximum. So if you want to know what the width of the central maximum is, you need just to figure out the distance between m equals 0 maximum and m equals 1 minimum, the destructive interference, and then double that distance. Because m equals 1 minimum is here, and the m equals 1 minimum is there on the other side. Here's the m equals 1 maximum. Here's the m equals 1 maximum. So again, here, if this is 0, m equals 1, m equals 2, m equals 1, m equals 2 maxima. The minima, m equals 1 minima will be here for the first one. M equals 2 minima there. M equals 3 minima there, and so on. So D and the wavelengths have to have the same units, so the units cancel. Put them in meters, or if they're the same unit, the units will just cancel. You can solve for the angle and figure out what angle this occurs at. If you know this angle and you know how far apart the screen is, it's just trigonometry to figure out how far from the middle you'll have those maxima or minima. It's just a triangle.